Why do alkanes react only in UV light while alkyl halides they react instantly with nucleophiles? The secret lies in their bond. And today I will reveal why alkanes undergo free radical substitution reactions while alkyl halides they prefer nucleophilic substitution. Hi, I am Dr. N. Swati. Stick with me till the end so that you will never forget this concept. Welcome back, chemistry lovers. In this video, I am decoding the reactivity difference between alkanes and alkyl halides. By the end, you will know exactly when a reaction proceeds by free radical substitution and when it goes by nucleophilic substitution. Alkanes are the saturated hydrocarbons containing carbon-carbon and carbon-hydrogen single bonds. They are having the general formula of CnH2n plus 2. Methane, ethane, propane and butane are the examples for alkanes. Alkyl halides are the derivatives of alkanes, where one of the hydrogen in alkanes is replaced with halogen. And they have general formula of CnH2n plus 1 X. Here X can be chlorine, fluorine, bromine or iodine. Methyl chloride, ethyl bromide and isopropyl chloride are few examples for alkyl halides. Now let us consider the bonding and polarity differences between alkanes and alkyl halides. So here I have given prototype compounds, methane for alkanes and methyl chloride is an example for alkyl halide. All the bonds present in alkanes, that is carbon-carbon and carbon-hydrogen bonds, are single bonds and they are sigma bonds. In these bonds, there is neither creation of partial positive charge nor partial negative charge. Hence, these bonds are said to be non-polar in nature. Due to the presence of non-polar carbon-hydrogen covalent bonds, these alkanes are considered to be inert and they are very much stable. When it comes to alkyl halides, the carbon-halogen bond present in alkyl halides is polar in nature because here this bond is shared between two atoms which have differences in their electronegativity. So chlorine electronegativity is more when compared with carbon. Due to this, the bonded pair of electrons is more distorted towards chlorine. Hence, chlorine gets partial negative charge and carbon, which is attached to halogen, gets partial positive charge. And that is how an electrophilic center will be created in alkyl halides. So the carbon, because it is having partial positive charge, it creates an electrophilic center, while the halogen, due to high electronegativity, it attains partial negative charge and thus it acts as a good leaving group. So that is how the carbon-hydrogen bonds, being non-polar in nature, alkanes are very much stable, while in case of alkyl halides, the carbon-halogen bond is being polar in nature, it creates electrophilic carbon in its structure. And this bonding difference is the reason why these molecules act differently. Now let's consider what type of reactions they will undergo. In case of alkanes, because they consist of non-polar covalent bond, they are inert in nature and they are very stable. So they need UV radiation or light to break carbon-hydrogen bonds. Upon breaking of these carbon-hydrogen bonds in the presence of UV light or heat, there will be generation of free radicals. That means alkyl radicals will be generated. Now to attain the stability, these alkyl radicals have to combine with another free radical. Hence, they will undergo free radical substitution reactions. Coming to alkyl halides, due to the presence of carbon-chlorine or carbon-halogen polar bond, there will be creation of electrophilic carbon. This electrophilic carbon will be acting as reactive site for nucleophilic attack. Hence, these alkyl halides, they will undergo nucleophilic substitution reactions. So, due to the presence of non-polar covalent bonds, alkanes undergo free radical substitution reactions in the presence of UV light or heat. While in case of alkyl halides, due to the presence of polar covalent bond, there will be creation of electrophilic carbon, hence they will undergo nucleophilic substitution reactions. Even though these two molecules are undergoing different type of reactions, one thing is common between their reactions. That is, they both are undergoing substitution reactions, but not addition reactions. Now let's find out why they will undergo only substitution but not addition. So in case of alkanes and alkyl halides, you can see there is structural similarity. So where one of the hydrogen in alkane, if you replace with halogen, that is chlorine, that will become corresponding alkyl halide. So both of these categories of molecules are having similar type of geometry. That is, the carbon is the central atom in both these molecules, which is in tetrahedral configuration having sp3 hybridization state. Now assume for these two molecules under this hybridization state, if they undergo addition reactions. So here in both these molecules, carbon is already having 4 bonds, that is, it is tetravalent in nature. Now in a typical reaction, if these molecules undergo addition, as a result of addition, one more atom or group will be added to this tetrahedral carbon, which makes the carbon pentavalent. Let us consider for methane here. So already 4 hydrogens are there, methane. So if one more group is attached, let us say X, then carbon becomes pentavalent. And pentavalent carbon is unstable. Same is the case even for methyl chloride also. Even methyl chloride upon addition reaction, that creates a pentavalent carbon which is highly unstable. So that is the reason they will undergo substitution, where one of the hydrogen in either alkyl halide or alkane can be replaced either with nucleophile or the free radical respectively, so that there will not be any disturbance in the hybridization state of the central carbon, which results in the formation of stable product. And this is the reason why alkanes and alkyl halides, they will undergo substitution rather than addition reactions. Now let me quickly revise the mechanism involved in free radical substitution reactions of alkanes, which I explained detailedly in one of my previous videos. So it involves 3 steps: initiation, propagation and termination. In initiation step, chlorine undergo homolysis in the presence of UV light or heat, and thus it generates 2 chloride radicals. These generated chloride radicals in the propagation step, they attacks alkane. So they will mainly cause again homolysis of carbon hydrogen bond which is present in alkanes, and thus the chloride radical will abstract hydride radical from the corresponding alkane. Thus there will be generation of hydrochloric acid, leaving the methyl radical aside. Now the formed methyl radical will be immediately associating with chloride radical in a coupling reaction, and thus results in the formation of methyl chloride as a substitution product. For more details about this reaction, you can check my previous video, link is given in the description. Now coming to the nucleophilic substitution reactions of alkyl halides, there are 2 types of nucleophilic substitution reactions are there, SN1 and SN2. Let me first explain about SN1. It is substitution nucleophilic unimolecular reaction, in short known as SN1. So this SN1 reaction involves 2 steps. First step is the formation of carbocation. Let's take ethyl chloride as an example. So ethyl chloride in the first step undergo heterolysis. So the carbon and halogen bond will be dissociated, okay, so that the bonded pair of electrons will be taken up by chlorine, thus resulting in the formation of chloride ion, while the carbon which is attached to the halogen becomes electron deficient. Thus there will be creation of carbocation. So when you consider ethyl chloride as an example, in the first step there will be formation of ethyl cation. Now in the next step, nucleophilic attack occurs. So here the nucleophile is hydroxide ion. So hydroxide ion will be attacking on the electron deficient carbon of the carbocation. So thus this hydroxide group will be attacking on the ethyl cation, and thus we get ethyl alcohol as the product. So these are the 2 steps involved in SN1 reaction, and in this carbocation formation is the rate determining step, because the overall rate of the formation of ethyl alcohol, that is the final product, it depends on how fastly and easily ethyl cation or the corresponding carbocation is going to form in the first step. Hence, this particular step is known as the rate determining step. Now, this SN1 reaction is favored in case of tertiary alkyl halides. Now, coming to the other mechanism, which is known as SN2, that is substitution nucleophilic bimolecular reaction. So, this SN2 reaction involves single step. So, here both attack of the nucleophile and leaving of halogen or halide ion takes place simultaneously. So here the nucleophile hydroxide ion will be attacking the alkyl halide from backside, that is 180 degrees away from the halogen. So here the halogen, that is chloride, is considered to be present on front side of the ethyl chloride, and the hydroxide group will be attacking exactly 180 degrees away from the 180 degrees away from the halogen. So here the attack of hydroxide group from backside and leaving of the chloride ion from the front side, they occur simultaneously. So thus there will be formation of ethyl alcohol as the product. So here this SN2 reaction is favored in case of primary alkyl halides. Why primary alkyl halides prefer SN2 reaction while tertiary prefers SN1 reactions? This I will be explaining in detail in my next video. Now let me quickly revise this topic, alkanes versus alkyl halides. So alkanes are the saturated hydrocarbons containing carbon-carbon and carbon-hydrogen single bonds, where the general formula is CnH2n plus 2. The bonds present in alkanes are non-polar covalent bonds, and they have the ability to generate free radicals whenever they are exposed to UV light or heat. Thus, the attacking groups on alkanes will be free radical, and hence they will undergo free radical substitution reactions. When it comes to alkyl halides, here they are considered to be derivatives of alkanes, where one or more than one of the hydrogens of alkanes will be replaced with halogen. Now let us say if one hydrogen is replaced with halogen, then they will be bearing the general formula of CnH2n plus 1x. And here, coming to the bonding differences, carbon-halogen bond present in alkyl halides is polar in nature, which creates electrophilic carbon. Thus, the attacking reagents on alkyl halides will be nucleophiles, and hence they will undergo nucleophilic substitution reaction. So overall, if you see alkanes, due to the presence of non-polar bonds, they will undergo free radical substitution reactions in the presence of UV light or heat. Where in case of alkyl halides, due to the presence of carbon-halogen polar bond, they attract nucleophiles. Hence, they will undergo nucleophilic substitution reactions. So I hope this video cleared your doubts about free radical substitution reactions of alkanes and nucleophilic substitution reactions of alkyl halides. If this video cleared your doubts, then give it a like and share it with your classmates. And don't forget to subscribe, because in my next video I'll cover deeper insights of SN1 and SN2 reactions. Thanks for watching and stay tuned to my channel.